Imagine a single grain of sand resting on the palm of your hand. It weighs almost nothing. You could lose it in the creases of your skin and never find it again. If you tipped your hand, you would not feel it leave. Now imagine that same grain moving at 133,000 miles an hour. At that speed, the air in front of it cannot get out of the way. The air compresses, and it heats, and it glows, and the grain begins to come apart from the outside in, one layer at a time, until there is nothing left of it at all. That is a meteor. Not a rock falling, a grain of dust taking the atmosphere apart in front of it and being taken apart in return. Tonight, in the second week of August, this will happen above you a few dozen times an hour. It has happened every August for at least 2,000 years. And every one of those grains came from the same place. We call them the Perseids because of where they appear to come from. If you watch for long enough, and if you trace each streak backward across the sky, the lines all seem to meet at a single point, low in the northeast, inside the constellation Perseus. They arrive from every direction. They all point back to one place. That is worth sitting with for a while. We will come back to that. Here is something else, and it is stranger than it sounds. Not one of these will reach the ground. Not one. They burn out somewhere between 50 and 80 miles up, in air so thin it barely counts as air, and nothing solid survives the fall. Whatever you see tonight, you will never be able to hold. So the dust arrives and the dust disappears, except that it does not really disappear. It goes somewhere. We will come back to that too. All of it came from one object, a comet named Swift-Tuttle, about 16 miles across, which last passed close to the Sun in 1992, and which will not come back until the year 2126. It is out there now, past the orbit of Neptune, moving very slowly in the cold. The dust it left behind is what you're watching. There is no hurry with any of this. The shower runs all night, and it runs for weeks, and the sky is not going anywhere. Neither are we.
Let us begin with the practical things, because they are calming, and because almost nobody tells you them properly. The night in question is the 12th of August, running into the small hours of the 13th. That is the peak, but the word peak is doing more work than it deserves here, and we will take that apart in a moment. The first thing worth knowing is what the moon is doing, because the moon decides almost everything about a meteor shower. A bright moon in the sky is a lamp left on in a dark room. It does not stop the meteors from arriving. It stops you from seeing most of them. In a normal year, the faint ones simply vanish into the glow, and you are left with only the brightest handful, and you come away thinking the shower was disappointing, when in fact it was only outshone. This year, there is no moon at all. The moon is new on the 12th of August. New moon means the moon is on the same side of the sky as the sun, rising with it and setting with it, and showing us its unlit face, which is to say, showing us nothing. It happens in the early afternoon on the east coast of the United States, which means that by the time the sky is dark that evening, the moon is already gone below the horizon with the sun, and it stays gone all night. So, the sky on the 12th is as dark as your particular patch of the world allows it to be. Whatever light pollution you have is the only light pollution you have. nothing is added. This is unusual, and it is the single best piece of news about this year. In most years, the timing is imperfect, and you take what you were given. The second thing worth knowing is where to look, and the answer is going to sound like a contradiction, so let us be careful with it. The meteors appear to come from the constellation Perseus, which is why they are called the Perseids. Perseus is a northern constellation, and in the second week of August, it clears the northeastern horizon in the late evening and then climbs slowly all night long. At 10 o'clock in the evening, it sits low, perhaps 15 degrees above the horizon, which is roughly the width of your outstretched hand and a half held at arm's length. By 1 in the morning, it is around 30 degrees up. By 3, 45. By 5, in the last hour before the sky begins to pale, it is nearly 60 degrees above the horizon and well clear of the murk that hangs over every horizon on Earth. The higher that point climbs, the more meteors you get. That is not a coincidence, and it is not folklore. When the radiant is low, the atmosphere is only intercepting a shallow slice of the incoming stream, and a great many meteors are happening below your horizon, where you cannot see them. When it is high, you are looking up into the full width of it.
So the shower is better after midnight. It is better still after 2. It is best in the hour or 2 before dawn. There is a second reason for that, and it is one of the most quietly satisfying facts in all of observational astronomy. Earth is moving around the Sun at about 66,000 miles an hour. It is also spinning. Put those two motions together, and you get something like a car driving through falling snow. The windshield collects far more snow than the back window does, because the windshield is the surface moving into the weather. The part of Earth facing forward along its orbit into the dust is the part where local time is somewhere between midnight and noon. In the evening, you are sitting on the back window. After midnight, the rotation of the planet carries you around onto the windshield. You are not waiting for the meteors to arrive. You are being turned to face them. The third practical thing is what you need to bring, and the honest answer is nothing. A telescope is worse than useless here. So are binoculars. Both work by narrowing your field of view in exchange for magnification. And a meteor is not an object you magnify. It is an event that happens somewhere across 180 degrees of sky, lasting under a second. And the only instrument suited to catching it is the one you already own. Your own eyes have the widest field of view of any optical system you will ever operate. What they need is time. Your eyes adapt to darkness in 2 stages. The pupil opens within a few seconds, which is the part you notice. The second stage is chemical, a slow rebuilding of a pigment in the retina called rhodopsin, and that takes 20 to 30 minutes to approach anything like completion. It continues improving more gradually for an hour or more after that. The important part is how easily it is undone. A single glance at a phone screen resets a good deal of it, and you begin again. This is why serious meteor observers use red light and nothing else. Red light does the least damage to dark adaptation, and a phone screen at full brightness does the most. So, the ritual is simple. Go outside, lie down or recline, because a meteor shower watched standing up becomes a study in neck pain within 10 minutes. Put the phone away. then wait half an hour without checking whether it is working. And here is one more piece of advice that runs against instinct. Do not stare at Perseus. Meteors near the radiant are coming almost straight toward you, which means you're seeing their paths end on, foreshortened into short stubs. The long, slow, beautiful streaks are the ones that appear well away from the radiant, where you are seeing the track from the side. 40 to 60 degrees away from Perseus is the sweet spot, and higher in the sky is better than lower, because you're looking through less air. Or, more simply, lie back, point your feet somewhere south, and look straight up. Now, expectations. And this is where most coverage of meteor showers becomes unhelpful.
You will read very large numbers. 100 an hour is the figure that circulates most often. That number is real, but it describes something specific and idealized, and we will come back to exactly what it means and why it is so often misquoted. What you can reasonably expect on the peak night from a genuinely dark rural site with the radiant high, after your eyes have adapted, is somewhere in the range of 30 to 60 meteors in an hour. From a suburban backyard, fewer. From inside a city, you may see 5 or 6 an hour, and every one of them will be a bright one. That still means one every minute or two. Sitting in the dark for an hour, that is enough. And they do not arrive evenly. This is the thing nobody warns you about. Meteors cluster in the way that raindrops on a windshield cluster, purely by chance. You will get 4 in 90 seconds, and then nothing for 11 minutes. The 11 minutes are not a sign that the shower has stopped. They are simply what randomness looks like from the inside, and the only correct response to them is to keep lying there. The last practical thing is that the peak is not a single night, and this is the part that takes the pressure off entirely. The Perseid stream is not a thin ribbon. Earth begins passing through its outer edges around the 17th of July and does not fully clear it until roughly the 24th of August. That is more than 5 weeks inside the same cloud of dust. The rate climbs slowly through late July, rises steeply through the first 10 days of August, reaches its maximum on the 12th into the 13th, and then falls away rather more quickly than it rose. So if the 12th is cloudy where you are, the 11th is good, the 13th is good, the 14th is worth going outside for. Even the 9th or 10th will show you something. Nothing about this requires you to be awake at a particular minute. And there is one more thing about this particular 12th of August, which is the sort of coincidence that sounds invented. The moon being new is what gives you the dark sky. But a new moon is not simply a moon that has gone away. It is a moon that has moved between Earth and the sun. Usually it passes a little above or a little below, and nothing happens, and we notice nothing at all. On the 12th of August in 2026, it does not pass above or below. That afternoon, across Greenland, Iceland, and northern Spain, the moon crosses directly in front of the sun, and for a couple of minutes the sky goes dark in the middle of the day. It is a total solar eclipse, the first visible from mainland Europe since 1999. The same moon, the same alignment, one event that takes the light away in the afternoon, and one that gives you the darkest sky of the year that night. Anyone standing in the path of that eclipse, looking up during the 2 minutes of totality, is looking at a genuinely black sky in the middle of the day at the height of the Perseids. Some of them will see one. So that is the night. A dark sky, a slow climb from the northeast, a planet turning you gently into the weather, and something like a meteor a minute if you are patient and somewhere unlit. What none of that tells you is what is actually burning. Because whatever you picture when you imagine the thing that makes a streak that bright across that much sky at that speed is almost certainly far too large. Take one of those streaks and slow it down. A Perseid crosses a good stretch of sky in something under a second. Some last half that. A few of the bright ones stretch to 2 or 3 seconds and feel at the time like a long while. Whatever your instinct tells you about the size of the thing producing that is wrong, and it is wrong by an enormous margin. The typical Perseid is a grain of dust between a millimeter and a few millimeters across. Call it the size of a grain of sand or a small breadcrumb or the head of a pin. It weighs a fraction of a gram. If it were lying on a table in front of you, you could brush it away without noticing you had done it. The bright ones, the ones that make people gasp and reach for a phone that is not fast enough, are the size of a pea. That is the whole inventory. Sand, and occasionally a pea. So the obvious question is how something that small produces something that bright. And the obvious answer, the one almost everybody carries around, is friction. The thing rubs against the air and it heats up, the way your palms warm when you rub them together. That answer is wrong. Not simplified, wrong. Here is what actually happens. The grain is moving at roughly 133,000 miles an hour. That's about 37 miles every second. At that speed, it is not passing through the air. The air in front of it cannot move aside quickly enough to get out of the way. Think about what it takes for air to get out of the way of something. The air has to be pushed, and that push travels outward through the air as a pressure wave. And a pressure wave in air is a sound wave. And sound moves at about 760 miles an hour at sea level, rather less in the thin, cold air high above. The air only knows something is coming if the news reaches it first. A grain doing 37 miles a second is arriving roughly 200 times faster than the news of its own approach. So the air does not part, it piles up. A thin cushion of gas forms directly in front of the grain and gets compressed into a tiny fraction of its original volume. And when you compress a gas that hard, that fast, it gets hot, extremely hot, thousands of degrees. The grain is not rubbing against anything. It is standing behind a wall of air that it is crushing, and the crushing is what makes the heat. Squeeze the air hard enough, and it burns. Then comes the second part, and this is where the light comes from. The grain does not glow because it is hot, in the way an iron poker glows. What happens is that the outer surface of the grain, sitting against that pocket of superheated gas, is heated so violently that it does not melt and it does not boil in any ordinary sense. It goes straight from solid to vapor. The surface layer is stripped away as gas, atom by atom, and the moment it leaves the grain, it is caught in that same compressed, screaming hot air. The word for this is ablation, and it is worth holding on to because it is one of the few genuinely essential words in this whole story. Ablation is a surface being carried away as vapor rather than being worn down or burned in place. The heat shield on a returning spacecraft works the same way, and on purpose. It is designed to be eaten from the outside in so that the energy goes into destroying the shield rather than into the crew. A meteoroid has no heat shield. It is its own heat shield, and it is a very small one. So, the grain is being peeled. Its own vaporized material streams away behind it into the compressed gas, and in that gas, the atoms are hit hard enough to knock electrons loose from them. An atom with an electron knocked off is called an ion, and a gas full of them is a plasma, which is what the inside of a fluorescent tube is, and what the surface of the sun is. Then the electrons fall back into place. Every time one does, it releases the energy it gained as a single flash of light at one precise color. Multiply that by an unthinkable number of atoms along a track 50 or 60 miles long in under a second. That is the streak, not a burning rock, a glowing column of air and vaporized dust briefly turned into plasma, marking out where the grain went. Which explains something you may have noticed and not thought about. The light is not the moving point. It is a line that appears all at once along its length and fades from one end. What you are seeing is not the object, it is the wake, and the wake is far larger than the thing that made it. A grain a millimeter across produces a glowing channel far wider than the grain itself and dozens of miles long. You are watching a hole being punched in the sky, and the hole is what glows. Now, where does this happen? All of it takes place between about 50 and 80 miles above the ground. Meteors begin to glow at the upper end of that band and are usually finished by the lower end. That region has a name, the mesosphere, and it is the least visited place on Earth. Consider what is above it and what is below it. Commercial aircraft cruise around 7 miles up. The highest balloons reach 25 or 30. The International Space Station orbits at about 250 miles, comfortably above the whole band. So the layer where every meteor you have ever seen burned up is too high for any aircraft or balloon to reach, and too low for any spacecraft to stay in. Anything that tries to orbit there will be dragged down within days. We have flown through it briefly, on the way up and on the way down. We have never stayed. It is sometimes called the ignorosphere, half as a joke, by the people who study it. The meteors are among the very few things that light it up from the inside and let us see what the conditions there are doing. And the air at that height is barely air. At 50 miles up, atmospheric pressure is around 1,000th of what it is at sea level. At 80 miles, it is roughly 1/1,000,000th. If you were standing there and you could ignore everything else that would be killing you, you would say without hesitation that you were in a vacuum. There is essentially nothing there. That is the substance that stops these things dead. A grain of sand arriving at 37 miles a second is destroyed completely by a gas so thin we would call it empty. Not slowed, not deflected, destroyed entirely in about a second, in a place where a good laboratory vacuum pump would struggle to do much better. Which brings us to the thing I said in the opening and which I want to be precise about now. Nothing from the Perseids reaches the ground, ever. Not rarely, not almost never. The Perseids have never produced a single recovered meteorite,
and the people who study this do not expect that they ever will. And there are two solid reasons for it. The first is speed. 60 miles a second of closing velocity is near the top end of what is physically possible for anything orbiting the Sun and meeting the Earth. And we will come to why the Perseids in particular are so fast. At that speed, the ablation is so violent that a grain simply does not survive long enough to slow down. Slow meteoroids sometimes do. Something entering at 8 or 10 miles a second has a chance of shedding its speed while there is still something left of it, and then falling the rest of the way as a cold, dark stone. That is where meteorites come from. Almost all of them are fragments of asteroids, and they arrive slowly by these standards. The second reason is what the grains are made of. Cometary dust is not rock in the way a pebble is rock. It is a loose, porous, fragile aggregate, closer in structure to a clump of cigarette ash than to a piece of granite. Some of these particles have a density lower than water. You could crush one between 2 fingers without effort if you could ever get hold of one.
Fast and fragile, the two worst possible properties for survival. So every Perseid you will ever see is a complete life. It begins glowing at 80 miles and it is finished by 50. And in between, it is entirely converted into light, heat, and a fine vapor that stays up there. You cannot catch one. You cannot own one. Whatever falls on the 12th of August has already stopped falling before it gets anywhere near you, and it never had any intention of arriving. That vapor does not leave, though. It has nowhere to go. It is still up there, and it is doing something, and it will be a while before we get to what. For now, hold on to the number, 50 to 80 miles, and nothing lower. Because there is still that other business from the opening. All of these grains are arriving on parallel courses from every part of the sky, and they all point back to the same spot in Perseus. Nothing is aiming them. There is no spot. Here is the picture that has been waiting since the opening. Stack a whole night of meteors into a single image, and something appears that no single meteor ever shows you. Every track drawn backward meets in one place. Not approximately, not near enough. They converge on a patch of sky a few degrees across, sitting inside the constellation Perseus. And they do it every year, and they have done it for as long as anyone has been keeping records. Which looks, unavoidably, like the meteors are coming out of a hole. They are not. There is nothing there. The point is empty, and the reason it appears at all is one of the oldest tricks in human vision. Stand between 2 rails and look down the line. The rails are parallel. You know this without checking because a train runs on them, and a train would not run on rails that met. And yet the picture in front of you shows 2 lines that converge. And if the ground is flat enough, they converge at a single point on the horizon. Nothing is bending. The rails are exactly as far apart a mile away as they are under your feet. What you are seeing is what parallel lines look like when you are standing inside them and looking along their length. Distance compresses everything toward a single vanishing point. And the vanishing point is not a place, it is a direction. The Perseid radiant is a vanishing point. The grains are traveling on paths that are very nearly parallel to one another.
They have to be, because they are all in the same orbit around the Sun, moving in the same direction at very nearly the same speed. They are spread across a volume of space millions of miles wide, so they are not close to each other in any meaningful sense, but their directions of travel are the same. Earth pushes into that stream. Every grain that meets the atmosphere arrives on the same heading. So you are standing inside a set of parallel lines, looking along them, and they appear to meet at a point. The point sits in Perseus for the simple reason that Perseus is the constellation toward which the Earth is moving.
Direction the stream is coming from, as seen from here at this time of year. The constellation has nothing to do with it. Those stars are hundreds of light years away and entirely uninvolved. It is a signpost, not a source. The radiant is not where the meteors come from. It is the direction you are being carried into. That single idea explains a run of things at once, which is how you can tell it is the right idea. It explains why meteors appear all over the sky and are still Perseids. A meteor 100 degrees away from Perseus, running clean across the top of the sky, is a Perseid if its track points back to that spot. The radiant does not constrain where a meteor appears, only where it points. It explains the foreshortening from the last section. A grain arriving from almost exactly the direction of the radiant is coming nearly straight at you, and you see the short stub because you are seeing a 50-mile path end on. A grain arriving from well off to the side is crossing your view, and you see the whole length of it. That is why the long, slow, elegant ones happen far from Perseus, and it is why the advice was to lie back and look up, rather than stare at the constellation. And it explains why the shower has a season at all. The stream sits in a fixed place relative to the Sun. Earth reaches that place in the second week of August, and nowhere else in the year. It is not that the meteors turn on, it is that Earth arrives. There is one more thing the vanishing point tells you, and it is subtler. The radiant moves. Not quickly, about 1 degree east each day, which is roughly 2 moon widths. Over the 5 weeks of the shower, it drifts a fair distance across the sky, which is why the radiant on the 20th of August is not quite where it is on the 12th of August. Observers who count meteors properly have to account for this, and the drift is tabulated to the day. The cause is straightforward once you see it. Earth is moving around the Sun, so the angle at which we meet the stream changes a little every day, the way the apparent direction of falling rain changes as a car speeds up or slows down. The rain is doing the same thing. Your motion through it is what changes, which is worth noticing for what it means. That 1 degree a day is not the meteors doing anything. It is a measurable, visible consequence of the fact that we are moving. You can watch the planet's motion written into the sky if you are patient enough to notice where the streaks were last week. Now, the constellation itself, since we've been using its name for 20 minutes. Perseus is a northern constellation, catalogued by Ptolemy in the 2nd century and known long before that. It sits between Cassiopeia and Auriga, and from the mid-northern latitudes, it never sets. In August, it is a late-night constellation, climbing through the small hours, and in winter, it is overhead in the early evening. The radiant sits in its northern part, close to a star called Eta Perseus, and very close to something worth turning your eyes towards while you are waiting. Between Perseus and Cassiopeia, there is a faint smudge that looks, to the unaided eye from a dark sight, like a piece of the Milky Way that has been rubbed with a thumb. That is the double cluster. Two open star clusters, each containing hundreds of hot young stars, sitting near each other in the same arm of the galaxy, about 7,500 light-years away. They are among the very few deep sky objects you can see without any instrument at all, and they happen to sit within a few degrees of where every Perseid points. If you are lying in a field waiting for the next meteor, that smudge is the thing to look at in the gaps. The brightest star in the constellation is Mirfak, and the second brightest is Algol. And Algol has a story that fits this film. Algol dims. Every 2 days and 21 hours, it fades noticeably for a few hours and then returns. It does this because it is not one star, but two, orbiting closely, and the dimmer one passes in front of the brighter one on every circuit. It is an eclipsing binary, and it was the first one ever identified by John Goodricke in 1783, who was 18 years old at the time and worked it out from naked eye observations alone. The name comes from Arabic, and it means the demon's head. In the Greek figure, Perseus is holding the severed head of Medusa, and Algol is the head, and the eye in the head is a star that blinks. Whether anyone before Goodricke understood why it blinks, nobody can say. But several cultures independently placed something unsettling at that exact position. And there is a persistent, contested argument that some ancient records preserve the period. Interesting, unproven. We will let it stay that way. The Perseids have an older name too, and it belongs to a different tradition entirely. In parts of Catholic Europe, they were called the Tears of St. Lawrence. Lawrence was a deacon in Rome, executed in the year 258, and his feast day is the 10th of August, which falls in the strongest part of the shower every single year without fail. The meteors were understood as his tears, returning annually. The astronomy in that is better than it first appears. Somebody noticed that this happens in the same handful of nights every year, reliably enough to attach to a fixed date in a calendar. That is a genuine observation, correctly made, centuries before anyone had any idea what a meteor was. And the earliest surviving record of the shower is older still. Chinese observers logged an unusual number of meteors in the year 36, and that account is generally taken as the first written appearance of the Perseids. Nearly 2,000 years of people looking up in the same week. So the point in Perseus is an illusion of perspective. The constellation is a coincidence of direction, and the whole thing is a signpost that happens to be on the right fence.
But the direction is real. The stream is real. It sits in a fixed place crossing Earth's orbit, and it has been sitting there long enough for people in the 2nd century to notice it, and long enough for the 12th of August to become a date. Which raises a question that nobody was in a position to ask until the middle of the 19th century. If the dust is in an orbit of its own, going around the sun on a fixed path that we happen to cross, then something put it there. Something was on that orbit first. In 1862, two men on opposite sides of the state of New York found it within 3 days of each other, and neither of them had the faintest idea what they were looking at.
In the summer of 1862, the United States was in the second year of its Civil War, and a hardware dealer in Rochester, New York, was in the habit of climbing onto a roof at night with a telescope. His name was Lewis Swift. He was 42 years old. He sold ironmongery for a living, and he had no formal training in astronomy of any kind, which was less unusual then than it sounds now. A great deal of 19th century astronomy was done by people who had a day job and a clear head and access to a dark sky. And in 1862, the sky over an American city was still genuinely dark. The roof he used belonged to a cider mill. On the 16th of July, Swift found a comet. He was not looking for it particularly, and when he saw it, he did what a careful amateur does, which is to distrust himself. There was already a comet in the sky that season, one that had been announced some weeks earlier, and Swift concluded that what he had found was that comet, already known, already claimed, and not worth reporting. So he wrote it down, and he did nothing. He waited 3 days. On the 19th of July, 400 miles east, an assistant at Harvard College Observatory in Cambridge, Massachusetts, found this same object independently and reported it at once. His name was Horace Parnell Tuttle. He was 25, he was a professional, and he was in exactly the right institutional position to have his observation taken seriously and circulated quickly. The report went out. The comet was announced. Swift, reading the announcement, realized what he had done. The object he had dismissed as somebody else's comet was nobody's comet. It had been his for 3 days, and he had talked himself out of it. To his considerable credit, he said so publicly, with his dates and his notes. And to the credit of the astronomical community of the time, the claim was accepted. Both names went on it. That is how it comes down to us. Swift Tuttle, a man who found it first and did not believe himself, and a man who found it second and picked up a pen. The comet itself was a good one. Through August and into September of 1862, it brightened until it was about as bright as Polaris, easily visible to the naked eye from a city, with a tail that stretched a substantial way across the sky. There were drawings of it. There are engravings in the illustrated papers of the period, printed alongside war news, which is a strange pairing to look at now. And here's the part that nobody in 1862 put together. The comet reached its best in the second half of August, which means that in the second week of that month, while the comet hung in the northern sky with its tail out, the Perseids were falling as they do every year, and the two things were visible at the same time on the same nights to the same people. Nobody connected them. There was no reason to. The comet was one kind of object, and a meteor was another. And the idea that the second could be made of the first had not yet been thought. It's worth sitting with how recent all of this is. 2,000 years of people watching the same nights, a saint's feast day built around them, Chinese records from the year 36, and in 1862, with a bright comet and a meteor shower sharing the same sky, the best astronomers alive still had no idea that they were looking at one thing. The answer arrived 4 years later. But before we get there, the two men deserve the rest of their lives because they're both worth knowing about. Lewis Swift kept going, and he got very good. He went on to discover a long series of comets over the following decades, enough to make him one of the most productive comet hunters of the 19th century, and he compiled catalogs of nebulae running to 1,000 entries. The hardware store eventually fell away. A wealthy patron in Rochester built him an observatory, and he ran it, and he became a public figure of a kind that doesn't really exist anymore. A self-taught man in a small American city whose name appeared in newspapers because of what he had found in the sky. In his 70s, he moved to Southern California to work at an observatory on Echo Mountain above Pasadena, where the air was steadier and the winters were kinder.
He kept observing until his eyesight failed, and he died in 1913 at the age of 93. He's one of those figures who makes the history of astronomy feel more accessible than it usually does. He was a shopkeeper on a cider mill roof, and then he wasn't. Horace Tuttle went the other way, and his story is stranger and considerably less tidy. Before 1862, he had already put his name on two other comets that matter enormously to this subject. One is the comet now called Tempel-Tuttle, which is the parent of the Leonid meteor shower, the November shower that produces the great storms. The other carries his name alone. Stop on that for a moment. The two most famous meteor showers in the northern sky, the August Perseids and the November Leonids, both trace back to comets with Tuttle's name attached to them, and he found them both before anyone understood that comets and meteors had anything to do with each other. He had his hands on the answer twice and did not know there was a question. Then the war took him. He left the observatory and enlisted, and he served in the Union forces through the remainder of the conflict. Then he was a competent officer by all accounts. He was present at engagements. He came back. Afterward, he stayed in the service and was given responsibility for money, which turned out to be a mistake. In the 1870s, he was marshal-coded for the misappropriation of government funds and dismissed. The rest of his life was spent in relative obscurity, doing some observing, holding minor positions, and he died in 1913 and was buried in a grave that went unmarked for the better part of a century. A headstone was eventually placed by people who thought he'd heed. It's a difficult story to file. He found the parent bodies of the two great meteor showers of the northern year, and he ended in disgrace over an accounting matter. And both of those things are true at once, and neither cancels the other. The comet doesn't care either way. It carries both names, and it will carry them as long as we keep records. There's one more thing about 1862 that will matter later, and I want to plant it now rather than surprise you with it. When astronomers of the period worked out the comet's orbit from their observations, they found something that raised an eyebrow. The path it followed brought it very close indeed to the path that Earth follows. Not in the sense that the two objects would meet, close in the sense that the two orbits, drawn as loops in space, come almost to touching. At the time, this was a curiosity, noted and set aside. It stopped being a curiosity in the 1990s, and we'll get to that, and it's one of the better stories in all of modern astronomy. For now, hold the position we're in. By the end of 1862, humanity possessed both halves of the answer and did not know it. There was a well-observed comet with a computed orbit that ran extremely close to our own, and there was a meteor shower on record for 18 centuries arriving from a fixed direction in the second week of every August. The two facts sat in the same journals, printed within pages of each other, and nobody laid one on top of the other. It took 4 years, and it took a man in Italy who was thinking about something else entirely, and when he did it, he not simply solved the Perseids, he ended the idea that meteors were weather and began the idea that they are the remains of something.
In the summer of 1862, the United States was in the second year of its Civil War, and a hardware dealer in Rochester, New York, was in the habit of climbing onto a roof at night with a telescope. His name was Lewis Swift. He was 42 years old. He sold ironmongery for a living, and he had no formal training in astronomy of any kind, which was less unusual then than it sounds now. A great deal of 19th century astronomy was done by people who had a day job and a clear head and access to a dark sky. And in 1862, the sky over an American city was still genuinely dark. The roof he used belonged to a cider mill. On the 16th of July, Swift found a comet. He was not looking for it particularly, and when he saw it, he did what a careful amateur does, which is to distrust himself.
There was already a comet in the sky that season, one that had been announced some weeks earlier, and Swift concluded that what he had found was that comet, already known, already claimed, and not worth reporting. So he wrote it down, and he did nothing. He waited 3 days. On the 19th of July, 400 miles east, an assistant at Harvard College Observatory in Cambridge, Massachusetts, found this same object independently and reported it at once. His name was Horace Parnell Tuttle. He was 25, he was a professional, and he was in exactly the right institutional position to have his observation taken seriously and circulated quickly. The report went out. The comet was announced. Swift, reading the announcement, realized what he had done. The object he had dismissed as somebody else's comet was nobody's comet. It had been his for 3 days, and he had talked himself out of it. To his considerable credit, he said so publicly, with his dates and his notes. And to the credit of the astronomical community of the time, the claim was accepted. Both names went on it. That is how it comes down to us. Swift Tuttle, a man who found it first and did not believe himself, and a man who found it second and picked up a pen. The comet itself was a good one. Through August and into September of 1862, it brightened until it was about as bright as Polaris, easily visible to the naked eye from a city, with a tail that stretched a substantial way across the sky. There were drawings of it. There are engravings in the illustrated papers of the period, printed alongside war news, which is a strange pairing to look at now. And here's the part that nobody in 1862 put together. The comet reached its best in the second half of August, which means that in the second week of that month, while the comet hung in the northern sky with its tail out, the Perseids were falling as they do every year, and the two things were visible at the same time on the same nights to the same people. Nobody connected them. There was no reason to. A comet was one kind of object, and a meteor was another. And the idea that the second could be made of the first had not yet been thought. It's worth sitting with how recent all of this is. 2,000 years of people watching the same nights, a saint's feast day built around them, Chinese records from the year 36, and in 1862, with a bright comet and a meteor shower sharing the same sky, the best astronomers alive still had no idea that they were looking at one thing. The answer arrived 4 years later. But before we get there, the two men deserve the rest of their lives because they're both worth knowing about. Lewis Swift kept going, and he got very good. He went on to discover a long series of comets over the following decades, enough to make him one of the most productive comet hunters of the 19th century, and he compiled catalogs of nebulae running to 1,000 entries. The hardware store eventually fell away. A wealthy patron in Rochester built him an observatory, and he ran it, and he became a public figure of a kind that doesn't really exist anymore. A self-taught man in a small American city whose name appeared in newspapers because of what he had found in the sky. In his 70s, he moved to Southern California to work at an observatory on Echo Mountain above Pasadena, where the air was steadier and the winters were kinder. He kept observing until his eyesight failed, and he died in 1913 at the age of 93. He's one of those figures who makes the history of astronomy feel more accessible than it usually does. He was a shopkeeper on a cider mill roof, and then he wasn't. Horace Tuttle went the other way, and his story is stranger and considerably less tidy. Before 1862, he had already put his name on 2 other comets that matter enormously to this subject. One is the comet now called Tempel-Tuttle, which is the parent of the Leonid meteor shower, the November shower that produces the great storms. The other carries his name alone. Stop on that for a moment. The 2 most famous meteor showers in the northern sky, the August Perseids and the November Leonids, both trace back to comets with Tuttle's name attached to them, and he found them both before anyone understood that comets and meteors had anything to do with each other. He had his hands on the answer twice and did not know there was a question. Then the war took him. He left the observatory and enlisted, and he served in the Union forces through the remainder of the conflict, and he was a competent officer by all accounts. He was present at engagements. He came back. Afterward, he stayed in the service and was given responsibility for money, which turned out to be a mistake. In the 1870s, he was marshal-coded for the misappropriation of government funds and dismissed. The rest of his life was spent in relative obscurity, doing some observing, holding minor positions, and he died in 1913 and was buried in a grave that went unmarked for the better part of a century. A headstone was eventually placed by people who thought he'd. It's a difficult story to file. He found the parent bodies of the two great meteor showers of the northern year, and he ended in disgrace over an accounting matter. And both of those things are true at once, and neither cancels the other. The comet doesn't care either way. It carries both names, and it will carry them as long as we keep records. There's one more thing about 1862 that will matter later, and I want to plant it now rather than surprise you with it. When astronomers of the period worked out the comet's orbit from their observations, they found something that raised an eyebrow. The path it followed brought it very close indeed to the path that Earth follows. Not in the sense that the two objects would meet, close in the sense that the two orbits, drawn as loops in space, come almost to touching. At the time, this was a curiosity, noted and set aside. It stopped being a curiosity in the 1990s, and we'll get to that, and it's one of the better stories in all of modern astronomy. For now, hold the position we're in. By the end of 1862, humanity possessed both halves of the answer and did not know it. There was a well-observed comet with a computed orbit that ran extremely close to our own, and there was a meteor shower on record for 18 centuries arriving from a fixed direction in the second week of every August. The two facts sat in the same journals, printed within pages of each other, and nobody laid one on top of the other. It took 4 years, and it took a man in Italy who was thinking about something else entirely, and when he did it, he not simply solved the Perseids, he ended the idea that meteors were weather and began the idea that they are the remains of something.
To understand what happened in 1866, you have to go back another 33 years to a night in November when a large part of the United States woke up frightened. On the morning of the 13th of November, 1833, meteors fell over North America at a rate that nobody had ever recorded and that nobody has seen since in quite the same way. Estimates made afterward ran into the tens of thousands per hour. Some accounts put it higher. The sky was described as full continuously for hours, from midnight until the light came. People were woken by neighbors. Some prayed. Some wrote it down carefully, which turned out to be the important response. Among those who wrote it down was Denison Olmsted, a professor at Yale, and what he did next is the beginning of meteor science as a subject. Olmsted gathered accounts from across the country, which in 1833 meant writing to people and waiting for the post. And when he laid them side by side, he found something the individual observers could not have seen. Observers in different states, hundreds of miles apart, had all described the meteors as coming from the same region of sky, and that region had stayed in the same place among the stars all night while the whole sky turned beneath it. That second detail is the one that settles it. If the meteors were a phenomenon of the atmosphere of the sort that weather is, the source would have stayed fixed relative to the horizon. It did not. It moved with the stars. Meteors stopped being weather that night. That was the first radiant ever identified, and everything in Section 3
The vanishing point and the parallel paths follows from what Olmsted worked out from letters. The Leonids came back in 1866, storming again over Europe, and by then astronomers had two things they had not had in 1833. They had the concept of a radiant, and they had a growing sense that the Leonids returned on something like a schedule, roughly every 33 years, with lesser showings in between. Something in an orbit, something with a period. Giovanni Virginio Schiaparelli was 31 years old and running the observatory at Brera in Milan. His name reaches most people, if it reaches them at all, through Mars. He is the man who mapped the Martian surface in the 1870s and labeled certain features canali, meaning channels, a word that was translated into English as canals, with consequences that ran for the better part of a century and produced a great deal of nonsense that was not his fault. This came first, and it is the better work. What Schiaparelli did in 1866 was arithmetic, and the arithmetic was not the hard part. The hard part was deciding it was worth doing. He took the radiant of the August shower, and he took the drift of that radiant across the weeks, and he combined them with the velocity at which the meteors seemed to be arriving. And from that, he calculated the orbit that a particle would have to be on in order to produce what observers were seeing. He got an ellipse, a long one, tilted steeply out of the plane that the planets move in, running out far beyond the outer solar system and coming back in. Then he compared it with the orbit that had been computed 2 years earlier for Swift's and Tuttle's the comet Tuttle had found some years before. 2 showers, 2 comets, 2 matches. One conclusion made twice, which is what makes it convincing rather than lucky. Take a moment on what that actually says, because it is easy to nod at and harder to feel. A comet is a body of ice, dust, and rock, spending most of its existence in the deep cold when nothing happens to it. When its orbit brings it near the sun, the ice on and just below its surface does not melt. It sublimates. It goes directly from solid to gas, the way dry ice does, and that gas rushes off the surface into vacuum, and it carries embedded dust with it. The gas escapes. The dust, being heavier and slower, mostly does not escape the comet's orbit. It drifts away from the nucleus at a walking pace, a few feet per second, and then it simply continues around the sun on very nearly the path the comet was already on. And if that orbit happens to cross ours, then once a year, at the same point in our own loop, we drive through it. That is the whole mechanism. That is the Perseids. The comet is not present. It hasn't been near the inner solar system since 1992 and will not be again until 2126. It doesn't need to be. It left the material along the road, and the road stays where it is, and we come back to the same intersection every August. The shower is not a visit, it is a wake in both senses of the word. Schiaparelli published this across 1866 and 1867, and the reception was fast and warm because the evidence did not require anyone to take anything on faith. The orbits were published. Anyone competent could check them. Within a few years, the idea that meteor showers are the debris of comets became the standard understanding, and it has remained the standard understanding ever since, refined enormously in its details and never overturned in its substance. That's 160 years, which for a scientific idea about the sky is a very long, unbroken run. He wasn't working alone in the general sense. Several people were circling the same question, and the connection between the Leonids and their comet was arrived at more or less simultaneously by others. Priority in this period is genuinely tangled, and honest historians of the subject say so. What is not in dispute is that Schiaparelli did the full calculation, published it clearly, and made the case in a form that convinced people. There is one consequence of all this that is worth stating plainly, because it changes what you are looking at when you go outside. Every meteor in the shower is a piece of the comet, not a piece of something like the comet, a piece of that specific object, 16 miles across, currently somewhere beyond the orbit of Neptune, which released that particular grain on some particular pass near the Sun, possibly a few centuries ago, possibly a good deal earlier. The grain has been going around the Sun on its own ever since, on a loop taking well over a century each time, out into the cold and back, over and over, until this August when it met a planet. You're watching a comet come apart in slow motion, one grain at a time, across thousands of years. And that's where the last 3 sections have been heading. We started with a streak of light and we found a grain of sand. We found the grain was traveling with a great many others on parallel paths. We found the paths belonged to an orbit, and we have now found what was on the orbit first, which leaves the object itself, and the object is worth meeting properly. It has a formal designation, 109P, and the P means periodic, and it means we have seen it come back. It is the largest object that repeatedly comes close to the Earth. Its orbit runs the wrong way around the Sun, which is the reason its dust arrives at us so violently. It has been observed and recorded, as it turns out, long before 1862 by people who had no idea they were watching the same thing return. And in 1992, when it came back on schedule, after 130 years away, it arrived 17 days late. That sounds like a footnote. It was not a footnote. It caused 4 years of very serious concern among people who do not concern easily.
This is the only photograph in this film of the thing that makes all of it. It was taken in the winter of 1992, when the comet came back after 130 years away. And it is not a good photograph by modern standards. It is grainy and small, and it looks like a smudge with a faint tail, because that is what it was from here. No spacecraft has ever been sent to it. Nobody has ever seen its surface. We have never had a close look at the object that produces the most reliably watched meteor shower on Earth, and we will not get one in the lifetime of anybody now living. What we have instead is arithmetic, and the arithmetic is remarkably good. The nucleus is about 16 miles across. That is the number to hold on to. 16 miles is the length of a large city. It is a solid body of ice and dust and rock, roughly that wide in every direction, dark as fresh asphalt, turning slowly on its axis about once every 2 3/4 days. 16 miles does not sound like much when the surrounding subject is the solar system. So here is the comparison that gives it weight. The object that struck the Earth 66 million years ago, the one that ended the age of the dinosaurs, is generally estimated at somewhere between 6 and 9 miles across. Swift-Tuttle is roughly twice that. Now, the orbit, because the orbit is where this object becomes genuinely unusual rather than merely large. It goes around the Sun once every 133 years. At its closest, it comes just inside the orbit of Earth, a little under 90 million miles from the Sun. At its farthest, it reaches about 51 times the Earth-Sun distance,
which puts it well beyond Neptune, out past the orbit of Pluto, in a part of the solar system where sunlight is 1,000th of what it is here, and the surface temperature is close to the temperature of empty space. It spends almost the whole of those 133 years out there. The visit to the inner solar system is brief, a couple of years of activity around the closest approach, and then a slow climb back into the dark that takes over 60 years, followed by a fall back inward that takes as long again. For most of its existence, nothing at all happens to it. Then there is the tilt, and the tilt is the important part. All the planets orbit the Sun in roughly the same flat plane, going the same way around. If you looked down on the solar system from above, everything would be turning counterclockwise, more or less, in a disk. That is not a rule of nature. It is a memory. It is left over from the flattened cloud of gas and dust the whole system formed out of 4.5 billion years ago, and everything that formed in that disk kept the disk's motion. Swift-Tuttle's orbit is tilted at about 113 degrees. An inclination above 90 degrees means something specific and rather striking. It means the object is going around the Sun the wrong way, not at an angle to the traffic, against it. It is driving the wrong way up the solar system. This is why the Perseids are so fast, and it resolves something left open in Section 2. Earth moves along its orbit at 66,000 miles an hour. The dust from Swift-Tuttle is moving at a comparable speed in its own orbit. But because that orbit runs against the direction of ours and steeply across it, we do not catch up to the dust, and we are not caught by it. We meet it close to head-on. The speeds add. The result is a closing velocity of roughly 133,000 miles an hour, which is near the upper limit of anything meeting the Earth while still bound to the Sun. The Perseids are among the fastest meteors that occur at all, and everything about them follows from that tilt. The brightness, the tendency to produce fireballs, the persistent trains, the fact that not one particle survives to the ground, all of it comes from the tilt. The single most visible property of the shower is a consequence of the direction the comet happens to be traveling. Now, how long we have known about it, which is more complicated and more interesting than 1862. Swift and Tuttle found it in 1862, but they were not the first to see it. They were the first to see it and record it in a way that let us compute an orbit and put a name on it. Once that orbit was known, and once its period was understood to be around 130 years, it became possible to run the clock backward and ask a specific question. Where would this object have been and how bright on each of its previous returns? And did anybody write anything down? The answer is yes, repeatedly, and the records are older than most nations. Chinese astronomers kept systematic sky records for a long time and kept them well, noting the appearance, position, brightness, and duration of what they called broom stars and guest stars. Those records survive. Working backward through the comet's orbit and comparing against those chronicles, astronomers have identified apparitions in the year 1862, in 1737, and then going much further back, in the year 188 and in 69 before the Common Era. The observation arc on this object runs to 2,000 years. That is an extraordinary thing to have. For most comets, we have a handful of returns at best.
For this one, we can point at a set of records made by people in the Han Dynasty and say with confidence that they were watching this object on this orbit on a pass it made 2,000 years ago, and that the same body came back and was photographed in 1992. And in the year 188, according to those records, it reached a brightness roughly equal to the brightest stars in the sky.
Which brings us to 1992 and to a detail that sits underneath the story of this comet and is easy to walk past. 133 years is longer than a human life. Nobody who watched Swift-Tuttle in 1862 was alive to see it in 1992. Lewis Swift died in 1913. Horace Tuttle died in 1923. Neither of them saw it come back, and neither of them could have. The comet they found returned 69 years after the last of them was buried. And nobody watching it in 1992 will see it in 2126. A child born the week it was recovered would be 134 years old. Each generation gets one look at it, or none. Most get none. It was recovered in September of 1992 by a Japanese amateur astronomer named Tsuruhiko Kiyuchi, observing with large binoculars. That deserves a moment. The largest object that comes anywhere near this planet on a regular schedule, absent for 130 years, awaited by professional observatories worldwide, was found on its return by an amateur with binoculars. The same tradition that found it in the first place from a cider mill roof in Rochester. It brightened through the autumn, reached its closest approach to the sun in December, and became an easy binocular object with a tail, and observers around the world tracked it as it went. It was, for a few months, the best-studied comet many of them had ever worked on. And there was a problem with it immediately that had nothing to do with how it looked. It was late. The prediction for when it would reach its closest point to the sun had been made carefully using the 1862 observations and the recovered older apparitions by people who were extremely good at this. The comet did not arrive when the predictions said. It arrived 17 days afterward. 17 days out of 133 years is a very small error. It is about 1 part in 3,000. In almost any other context, it would be a triumph of prediction rather than a failure. But this is an object 16 miles across on an orbit that comes within a whisker of touching our own, arriving head-on at 133,000 miles an hour. And the next return is in 2126. Somebody sat down and asked the obvious question. If it was 17 days late this time, what happens if it is late again next time? The answer, worked out in the last days of 1992, was published as a formal circular to the astronomical community, and it was not reassuring. I want to be careful with how this section goes, because the material in it was reported at the time in a tone I do not intend to use. This is a story with a worrying middle and a settled ending, and the settled ending is the point of telling it. Nothing here is unresolved. Nobody is currently concerned. If you are listening to this in order to fall asleep, this is a story about how a question got answered, and I will take it slowly. The man at the center of it is Brian Marsden, an English astronomer
who spent his career at the Smithsonian Astrophysical Observatory in Cambridge, Massachusetts, running the Minor Planet Center and the Central Bureau for Astronomical Telegrams. Those two institutions are the clearinghouse for exactly this kind of information. When somebody anywhere in the world finds a comet or an asteroid, the observation goes to that office and the orbit is computed and a circular goes out. For decades, Marsden was the person the world's astronomers called when an orbit needed to be nailed down, and he was very good at it. He was also the reason anybody was looking for Swift-Tuttle in 1992 in the first place. In the 1970s, Marsden went looking for earlier appearances of the comet in the historical record, and he found a good candidate. A comet observed in 1737, recorded in Beijing by a Jesuit astronomer missionary working at the imperial court. If that 1737 object was the same body, then the interval between it and 1862 gave a period, and the period gave a prediction. Marsden published one. He suggested the comet would come back around 1992. So when Kiyuchi found it in September of that year, it was not a surprise, it was a confirmation. The historical detective work had worked, and it had worked across 250 years. That matters for what follows, because the same method that predicted the return is the method that eventually settled everything else. Old records, carefully read, are a legitimate scientific instrument. But the prediction was 17 days off. Marsden's model said the comet should reach its closest point to the Sun around the 25th of November. It arrived on the 12th of December. 17 days is a small error in absolute terms, but it is not nothing. And the reason it happens is worth understanding because it's a permanent feature of comets rather than a mistake anyone made. A planet is a simple thing to predict. It is a solid body, and the only forces acting on it are gravitational, and gravity is very well understood, so you can compute where Neptune will be in 500 years and be confident. A comet is not simple because a comet leaks. When it comes near the Sun and the ice starts turning to gas, that gas leaves the surface in jets and the jets push back. A jet on one side gives the nucleus a small shove in the other direction, exactly as a rocket engine does, and the nucleus is being shoved this way and that for the entire time it is active. These are called non-gravitational forces, and they are tiny. Over a single pass, they change almost nothing you could measure directly. Over 133 years, they add up to 17 days. And they are not predictable in advance because they depend on where the active vents happen to be on the surface, which way the nucleus is facing, how the rotation is oriented, and how much ice is left in each spot. We cannot see any of that from here. So the 17 days was not an error in the calculation. It was the comet doing something we had no way it would do, which is where the question came from. Late in 1992, with the comet's actual position finally in hand, Marsden ran the orbit forward to the next return in 2126 and looked at what the geometry would be.
The two orbits come almost to touching. That was known in 1862 and noted as a curiosity. The minimum distance between the two paths is under 100,000 miles, which in these terms is essentially zero. A near miss is not the right phrase, because the paths do not miss. What separates the comet from the Earth is timing. We are simply not at the crossing point at the same moment. Timing is exactly the thing that just went wrong, by 17 days. So Marsden asked the question directly. If the 2126 perihelion is also displaced, and displaced by a similar amount, where does the comet end up on the 14th of August of that year, and where are we? The answer was that a further shift of about 2 weeks would put the comet and the Earth at the crossing point together. He published it. It went out as an astronomical circular in December of 1992, stated plainly, with the caveat attached that this was a conditional result, depending on a quantity nobody could yet constrain. The press did what the press does. Marsden, who was not a sensationalist by temperament, spent a good deal of the following period explaining that a conditional statement about a 15-day timing shift is not a prediction of an impact. But the honest position at the end of 1992 was that the possibility could not be excluded with the data available. Not because it was likely, because the orbit was not yet known well enough to rule it out. What was needed was more observations, and the useful observations were not going to come from telescopes because the comet was leaving and would not be back. They had to come from the past. This is where an American writer and amateur astronomer named Gary Cronk enters, and this is my favorite part of the story. Cronk is a historian of comets. He compiles and cross-references historical observations, which means sitting with translated chronicles and catalogs and working out which recorded object was which. He went looking for earlier returns of Swift-Tuttle beyond 1737 in the Chinese records, and he found two. A comet recorded in the year 180 of the Common Era, and another in 69 before it. He took them to Marsden, who checked them against the orbit and confirmed them. The effect of that was immediate and total. An orbit computed from observations spanning 130 years is one thing. An orbit computed from observations spanning 2,000 years is an entirely different object. Every one of those ancient sightings is a fixed point that the comet's path is required to pass through. And with points that far apart, the small non-gravitational drift is no longer an unknown. It becomes something you can measure directly, because you can see exactly how much it has accumulated across 15 returns. Marsden recomputed with the full arc. The 2126 passage is not a close call. On the 5th of August of that year, the comet passes about 14.2 million miles from Earth. That is roughly 60 times the distance to the Moon. It is a comfortable, unremarkable miss. And the orbit, once anchored across 2 millennia, is stable. The current position is that there is no danger from this object for at least the next 2,000 years. The question was raised in December, and it was answered within a few years. And it was answered by reading things that people wrote down 2,000 years ago because the sky looked unusual. There is one distant date that remains in the literature, and I will mention it because leaving it out would be dishonest, and because it is genuinely calming rather than otherwise. The calculations show a closer approach in the year 4479, and the estimated probability of an impact at that encounter is around 1 in a million. Beyond that, the orbit cannot be projected meaningfully because small uncertainties grow over that kind of span, and the per-orbit probability afterward is smaller still. 1 in a million, 2,450 years from now. For comparison, that is further into the future than the Roman Republic is into the past. Every language now spoken will have changed beyond recognition. Whatever is here then will have instruments we cannot imagine, and if it matters to them, a very long time to do something about it. It is not a problem. It is a note in a file kept by people who are thorough. So, the comet is safe, and the story is closed, and the 2126 return will be a spectacle rather than an event. Current expectations are that it will be a genuinely bright naked-eye comet of the sort that people remember for the rest of their lives. Which leaves the dust, because the comet is out beyond Neptune, and the road it left behind is still here, and we are still driving through it every August. That road is not uniform. It has thicker parts and thinner parts, and the thicker parts are not where they were a century ago, and something quite large has been moving them around. That is why this particular year, with its perfect moonless sky, is forecast to be a little disappointing.
The word stream keeps coming up, and it is a better word than it first appears, so let us take it seriously for a while. A river is not uniform. It has a fast channel and slow shallows. It has places where the current bunches and places where it thins out. It carries different material in different parts of its width, and if you crossed the same river at the same point every year for a century, you would not find it identical on any two crossings. The Perseid stream is like that, and for related reasons. Start with how it was built. Every time Swift-Tuttle comes near the Sun, which is once every 133 years, it becomes active for a couple of years and sheds dust. Each of those passes produces a fresh batch of material, and each batch leaves the nucleus at slightly different speeds and in slightly different directions. That matters more than it sounds. A grain that leaves a few feet per second faster than its neighbor ends up on a very slightly larger orbit, which means a very slightly longer period, which means after 10 circuits, it is somewhere quite different along the loop. So each pass produces not a cloud, but a filament, a narrow ribbon of dust spreading slowly on the orbit, which over a few centuries stretches into a long, thin arc and eventually wraps the whole loop. The stream is not one thing. It is dozens of filaments of different ages, all following the same road, overlapping and interleaved, laid down on separate visits going back thousands of years. Some of the dust you see on the 12th of August was released before the pyramids. Now, what moves them around? The grains are small enough that they do not simply follow gravity and nothing else. 3 things act on them, and all 3 are gentle, and all 3 are relentless. The first is sunlight, which has pressure. Light carries momentum, and when it lands on a grain, it pushes. The push is minute. On a boulder, it is irrelevant. On a particle a millimeter across, over centuries, it is not. And the smallest grains are gradually shepherded outward and eventually swept away entirely. This is why the very finest dust does not stay in a stream indefinitely. The second is a slower effect, in which a grain absorbs sunlight on one side and radiates that heat away as it turns, and the radiation carries a tiny recoil that acts against its motion. The result is that small particles spiral very gradually inward toward the sun over long timescales. It has a name, the Poynting-Robertson effect, and it is one of those forces that does nothing you would notice in 1,000 years and rearranges everything in 100,000. And the third is Jupiter. Jupiter is the largest object in the solar system apart from the sun, and everything that moves out here eventually has to account for it. Swift-Tuttle's orbit is locked to Jupiter's in a specific way,
For every 1 orbit the comet completes, Jupiter completes about 11. That's called a resonance, and a resonance means the two bodies keep returning to similar relative positions, which means the gravitational nudges don't average out over time. They repeat and they compound. The comet itself is massive enough to shrug this off, more or less. The dust is not. Every filament in the stream is being pulled and stretched by Jupiter on a cycle, and different filaments, laid down at different times and sitting at slightly different distances, get pulled by different amounts. Over centuries, this shifts them sideways across our path. A filament that Earth passed straight through in the 1860s may now sit slightly inside or slightly outside our orbit, so we clip its edge instead of its core. The dust does not change. Our line through it does. Which is why Perseid rates vary from year to year in ways that have nothing to do with the moon or the weather. There have been strong years. In 1991 and 1993, around the comet's return, observers recorded rates well above the normal, in some cases several times the usual level, because fresh, dense material released on that pass was still concentrated near the nucleus and had not yet spread along the orbit. Those were genuine outbursts, and they were correctly predicted in advance, which was one of the early successes of modeling this properly. There have been quiet years too, and less has been written about them because nobody publishes an article about a shower that behaved as expected. And now this year, which is the honest part of this film. Everything you will read about the Perseids in 2026 leads with the moon, and the moon is genuinely excellent. New moon on the 12th, no moonlight at any point in the night, the darkest possible sky for the peak. That's real, and it is unusual, and it's worth going out for. But the moon is only the 1-2 things that decide what you see. The other is how much dust is actually there. And the modeling for this year suggests we're passing through a relatively lean part of the stream. The International Meteor Organization's calendar for 2026 forecasts a background rate below the long-term average, in the region of 30 to 50 per hour at best under ideal conditions, rather than the 100 that gets quoted, with an expected return toward normal in the following year as Earth's path moves back into material that Jupiter has disturbed less. So this is a year with a perfect sky and a thin river. I want to be plain about why I am telling you that, rather than leaving it out. There's a version of this film that says nothing about the forecast, leads with the moonless sky, quotes 100 meteors an hour, and sends everybody outside expecting something they are unlikely to get. It would be more exciting for about 3 minutes, and then it would be a small betrayal, on the night, in the field, in the dark. 30 to 50 per hour under a genuinely dark sky with no moon at all is still a meteor roughly a minute or two, and every one of them visible rather than washed out. It's a good night. It is simply not the record-breaking night that some of the coverage is promising. There's one more layer to the forecast that's worth having, because it's the kind of prediction that would have been impossible 30 years ago. Modelers don't only estimate the general background rate, they compute where the filaments are, pass by pass, and check whether Earth's path passes near any of them in a given year. When it does, you get a short, sharp enhancement lasting an hour or two rather than a broad peak. For this year, there's a possible encounter with an older dust trail in the early hours of the 13th of August, in the window around 1 o'clock Universal Time, which is around 9 in the evening on the east coast of the United States and 6 in the evening on the west coast of North America. For most of North America, that falls before or around the start of true darkness, which is unfortunate timing, though the eastern half of the country may catch the tail of it as the sky finishes darkening. It may amount to nothing. Trail predictions of this kind are right often enough to be published and wrong often enough that nobody should plan an evening around one. The honest summary is this: go out on the 12th into the 13th, expect a meteor around a minute or two, be pleased if it is more. And there's a longer view worth holding, which puts a lean year in proportion. Swift-Tuttle has been shedding this material for thousands of years and has lost a negligible fraction of itself doing it. The stream is not running out, it is being redistributed endlessly by sunlight and by Jupiter and by the slow drift of everything in it, and the pattern of thick and thin years cycles on a timescale of decades and centuries. Models of the stream suggest richer years are ahead. Some project a substantially stronger return within the next few years as Earth's path crosses denser material. That is a projection rather than a promise, and it comes from the same kind of modeling that got 1993 right and has been wrong on other occasions. What is certain is that the river is still there, and that we keep crossing it every August, and that we will keep crossing it long after everybody now alive has stopped going outside to look. Which finally brings us back to the grains themselves, and to the two things left unanswered: the colors, because they are not all the same color, and the color tells you what the grain was made of, and the vapor, which has been sitting up there unaccounted for since we left it in the mesosphere a very long time ago. If you watch long enough on a dark night, you will notice that they are not all white. Most are, or near enough, because the faint ones do not give your eye enough light to register color at all. Color vision needs a certain brightness to work, and below that threshold, everything reads as pale gray. But the bright ones come through in color, and once you have seen it, you cannot unsee it. Green, yellow, occasionally orange or a hard blue-white at the head with something warmer trailing behind. Those colors are not decoration. They are a chemical analysis performed in the sky in real time on a grain of dust that no longer exists. Go back to what is happening in the track. The grain is being vaporized, and its atoms are being flung into superheated, compressed air, and they are being knocked about hard enough to lose electrons. Then the electrons drop back into place, and each time one does, it emits a single flash of light. The crucial part is that the color of that flash is fixed. It is not a matter of degree. Every element has its own set of allowed electron positions, and the gaps between them are exact, and the light released as an electron falls across a gap has exactly the energy of that gap, which means exactly one color. Sodium falls at a particular yellow, magnesium at a particular blue-green. Iron produces a dense thicket of lines across much of the visible range. Calcium, when it has lost an electron, sits in the violet. So the color of a meteor is a readout of its composition, not an inference, a direct measurement of what was in the grain. Every streak is a small, brief experiment, and the sky publishes the result immediately. The green that Perseids are known for is generally magnesium, and it's one of the more reliable identifiers of the shower. The yellow is sodium, which is the same element that gives old street lamps their particular yellow glow, working by exactly the same mechanism. Sodium sits in the outer layers of these grains, and it vaporizes early and easily, which is why the yellow often appears at the start of a track. Iron and calcium need more energy to excite, and they come through in the brightest events, which is one reason a fireball can look different in color from an ordinary meteor, even if it's made of the same material. It is not a different substance, it is more of it, hotter, revealing lines that a fainter meteor never reaches. And there is oxygen, which is not from the comet at all. A particular green line comes from oxygen atoms in our own upper atmosphere, excited by the passage of the meteor. Part of what you are seeing is the grain. Part of it is the air responding. This is not merely descriptive. Meteor spectroscopy is a working field, and it is one of the very few ways we have of sampling material from a comet without going to one. Point a camera at the sky with a diffraction grating over the lens, and any bright meteor that crosses the field is recorded as a spread of its own emission lines. Do that for enough events, and you can begin to characterize the composition of a particular stream, and compare one shower with another, and detect that the parent bodies are made of measurably different stuff. We've never sent a spacecraft to Swift-Tuttle. We never will within any horizon that means anything. But we have analyzed its material repeatedly because it delivers samples to the top of our atmosphere every August and destroys them in a way that broadcasts what they were made of. The only sample return mission we have to this comet is the shower itself. Now, the trains. If you catch a very bright one, sometimes the streak doesn't vanish. A faint glowing line hangs in the sky where the meteor was for a second or 10 or occasionally minutes. And if you keep watching, it bends, it curls, and drifts and comes apart, slowly, like smoke in still air. That is a persistent train, and the Perseids produce them more than most. What you are seeing is the aftermath. The meteor has left behind a column of air that has been ionized and chemically disturbed, and the recombination of that material continues to emit light for a while after the event. In the brightest cases, there is genuine chemistry involved, with ozone and atomic oxygen reacting in the disturbed column and glowing as they do. The drifting is the interesting part. That column is sitting at 50 or 60 miles up, in the region we called the least visited place on Earth. And it moves because the air up there is moving at speeds that would be a serious storm at ground level, which means a persistent train is a windsock in a layer of atmosphere we can't otherwise reach. Watching it deform is watching the wind at 60 miles altitude, drawn for you in glowing gas by an object that arrived from beyond Neptune. Researchers have used this exactly to measure upper atmospheric winds. It's a real technique, not a poetic aside. And then there are the fireballs, and this is what the Perseids are genuinely famous for. A fireball is defined simply. It's a meteor at least as bright as Venus, which is the brightest thing in the night sky apart from the moon. In practice, it means something that lights up the ground, casts a shadow, and makes people who were talking stop talking. The Perseids produce more of them than any other annual shower. There are two reasons, and both of them come from things established earlier in this film. The first is the speed. The energy available in a moving object goes as the square of its velocity, which means doubling the speed doesn't double the energy, it quadruples it. The Perseids arrive at roughly 133,000 miles an hour because of that retrograde orbit, and that's near the top of the possible range. So a Perseid grain carries far more energy than a grain of the same size arriving in a slower shower. More energy, more light. The second is that Swift-Tuttle is a large comet that has been shedding material for a very long time, and its stream contains a healthy population of larger particles. Pea-sized rather than sand-sized, rare, but present in numbers that smaller parent bodies can't match. Big grains, moving faster than almost anything else, hitting an atmosphere that stops them completely. That is a fireball. We keep count of these now systematically. NASA runs a meteoroid environment office at the Marshall Space Flight Center in Huntsville, Alabama. And among other things, it operates a network of all-sky cameras across the United States. Each one photographs the entire sky continuously through the night. When the same fireball is caught by two or more stations from different positions, the geometry gives you the true three-dimensional path. And from the path, you get the entry velocity, the altitude at which it began and ended, and running the trajectory backward out of the atmosphere, the orbit it was on before it arrived. Which means for a well-observed fireball, we can state from the ground which stream it belonged to, and therefore which comet it came from. The office's stated purpose is practical rather than aesthetic. Spacecraft have to be designed against this environment, and knowing how much material of what size is arriving and when is an engineering requirement. The beautiful part is a byproduct of a hazard assessment. There is one more thing about fireballs that catches people out, and it's worth knowing before the 12th. Sometimes you hear them. Not the sonic boom, which is real for very large events and arrives minutes later, having traveled at the speed of sound from 50 miles up. Something else, a faint hissing or crackling that observers report as simultaneous with the light, which should be impossible because sound can't travel 50 miles instantly. The leading explanation is that very bright fireballs emit radio waves, and those arrive instantly, and that they induce faint vibrations in objects near the listener. Hair,
Glasses, leaves, clothing. The sound is generated locally, right beside you, by radio energy from an event 50 miles overhead. It is called electrophonic sound. It was dismissed as imagination for a long time, and then it was recorded. So that is the full life of one grain. It leaves a comet somewhere beyond the orbit of Mars, drifting off at walking pace. It orbits the Sun alone for a few thousand years. It meets the top of our atmosphere at 133,000 miles an hour, and in less than a second, it is stripped to nothing, and the stripping broadcasts its chemistry as colored light, and sometimes leaves a glowing column that shows us the wind and a place we cannot go. And then it is gone. Except that it is not gone. That is the thing we have been carrying since the second section, and it is the last thing left. The grain is destroyed. The material is not. It cannot be. It is still up there, 50 miles above your head, in a form small enough that it will take years to come down. And when it does come down, it does something none of this has prepared you for. The grain is destroyed. The atoms are not. Nothing in the last 2 hours has removed a single atom from the universe. The grain was taken apart, and its material was vaporized into the thin air at 50 or 60 miles up, and it is still there. Vapor cools. Atoms find each other. And what forms out of that cooling vapor is a new kind of particle far smaller than the grain that produced it. We call it meteoric smoke. These particles are nanometer scale, which is to say a few millionths of a millimeter. A single grain of comet dust produces an enormous number of them. They are made of the metals that were in the grain, mostly iron, magnesium, and silicon, recondensed into something so small that the ordinary rules of falling barely apply. An object that small in air that thin does not really fall. It sinks on a timescale of months to years, drifting downward through the atmosphere at a rate that would be imperceptible if you could somehow follow one. So the mesosphere, that unvisited band, is permanently hazy with the remains of things that arrived from space. It has been accumulating this material continuously since as long as the Earth has had an atmosphere, and it is topped up every single day. Which brings us to how much arrives. Estimates vary because the measurement is genuinely hard, and different methods give different answers. Counting fireballs with cameras gives one figure. Measuring metal layers in the upper atmosphere by radar and laser gives another. Sampling the accumulation of extraterrestrial material in polar ice sheets and deep-sea sediment gives a third. The published range runs from around 40 tons a day at the low end to over 100 at the high end. Take somewhere in the middle and call it a few dozen tons of material arriving from space every day. Almost none of it is anything you would notice. The overwhelming majority is dust. Meteorites, the pieces that reach the ground intact, are a vanishingly small fraction of the total mass, and none of the Perseid material is among them. The Earth gains weight every day, quietly,
mostly as smoke. And now the thing I promised, which is what that smoke goes on to. There is a kind of cloud that forms higher than any other cloud on Earth. It sits at around 50 miles up in the coldest part of the entire atmosphere, and it can only be seen in deep twilight in summer from higher latitudes when the sun is below the horizon for the observer, but still lighting that layer from underneath. They are blue and finely rippled, like sand on a tidal flat, and they are called noctilucent clouds, which means night shining. They are made of ice, which raises an immediate problem. The mesosphere is extraordinarily dry. There is water vapor up there, but very little of it. And more importantly, water vapor doesn't simply freeze into a cloud on its own. It needs something to freeze onto. Every cloud in the lower atmosphere forms on particles of dust, salt, or pollution, and without those nuclei, the vapor stays vapor. At 50 miles up, there is no dust from the ground. Nothing from the surface reaches that height in any quantity. But there is meteoric smoke in enormous numbers, sinking slowly through exactly that layer. The evidence strongly indicates that these clouds form on the remains of meteors. Direct sampling by sounding rockets has found meteoric material inside noctilucent cloud particles, and the models work when you include the smoke and struggle when you leave it out. Which means the highest clouds in the sky are built around the ashes of comets. Every one of those ice crystals is wrapped around a speck of something that used to be part of a body in the outer solar system. The blue is sunlight scattering off ice that formed on the remains of Swift-Tuttle, and on the remains of a dozen other comets, and on material older than the sun that has been falling into this atmosphere for 4 billion years. You can see them from the northern United States, from Canada, from Britain, in June and July, in the last hour of twilight, looking north. Which is to say, the month before the Perseids, the sky is quietly showing you what became of the Perseids from the years before. And then, eventually, it comes down. The smoke sinks out of the mesosphere over months and years into the layers where weather happens, and there it does what every other small particle in the atmosphere does. It gets caught in a droplet, and the droplet joins others, and it falls. Cosmic dust comes down in rain. It has been doing so continuously since there was rain to come down in. It settles on roofs, on fields, on ice sheets, on the floor of every ocean. The deep sea floor accumulates so slowly and is disturbed so little that the extraterrestrial fraction in a sediment core is measurable. Polar ice does the same thing, layer by annual layer. Some of the best estimates of how much material arrives from space come from counting the tiny melted spherules left in ice that fell as snow. The dust is in the ice. It is in the deep sea floor. It is in the soil. It is, in some small measure, in the water in your house. There is a version of this fact that gets overstated, so let me be careful. You will sometimes hear that the dust from meteors is in your food and in your body, and that we are made of comets. The first part is true in the strict sense that a few dozen tons a day spread over the whole Earth ends up everywhere, in quantities so small they are difficult to detect and impossible to notice. The second part, we are made of stars, is true for an entirely different and much older reason, and the two should not be run together. The iron in your blood was made inside a star that died before the sun existed. That is not the same claim as the dust from this August's meteors. What is honestly true is smaller, and I think better.
A grain of comet dust burns up above your head in August. It becomes smoke. The smoke drifts down for a year or two and forms a cloud that somebody photographs in July, and then falls as rain and lands in a field. That is a real chain of events with nothing exaggerated in it, and it happens continuously, and it has been happening every August for the entire history of this planet. which lets us close the loop that opened at the beginning of this film. We started with a grain of sand in the palm of your hand. It is worth returning to now that everything else is in place. That grain left a body 16 miles across, somewhere out beyond the orbit of Mars, drifting away at walking speed some centuries ago. It went around the Sun on its own, out past Neptune and back, more than once, in the cold and the dark, entirely undisturbed for longer than most human institutions have existed. Then it met a planet on a specific night in August at 133,000 miles an hour and was taken apart in less than a second. And everything it was made of was converted into a single flash of colored light that somebody in a field looked up and saw. And then it became smoke and a cloud and rain and ground. The whole of that for one grain, and there will be dozens an hour. There is nothing you need to do about any of this. That is the last thing worth saying, and it is not a small one. The shower requires nothing from you. No equipment, no expertise, no plan, no particular hour. It is not an event that can be missed in the way a launch or an eclipse can be missed. It runs for 5 weeks. It is strongest on one night and good on the nights either side. And it will do the same thing next year. And it did the same thing in the year 36, when somebody in China wrote down that there were an unusual number of meteors. The comet will come back in 2126 and be bright and be watched by people who have not been born, and it will leave more dust on the same road, and the road will still cross ours in August. So on the 12th, if the sky is clear, go outside. Lie back somewhere the ground is flat and the light is low. Give your eyes half an hour without checking anything. Point your feet south and look straight up, and let the gaps be long, because the gaps are most of it. And when one crosses, remember what it actually is. Not a star, not a rock, not anything falling toward you. A grain of dust the size of a breadcrumb, 50 miles up, briefly turning the air into light. The shower is running now, whether or not anyone is watching it. That is true tonight, and it will be true on the 12th, and on the 13th, and on all the nights between. Somewhere over an ocean where nobody lives, meteors are entering the atmosphere at this moment and burning out at 60 miles and going unrecorded, as almost all of them always have. The comet is a very long way out. It's past the orbit of Neptune, in the part of its loop where it moves most slowly, barely faster than a walking speed against the background stars. There is no sunlight there to speak of. Nothing is subliming. Nothing is coming off it. It is simply cold and dark and turning once in 2 3/4 days, as it has been for the past 30 years. It has another century of that ahead before it starts to fall back inward. And in 2126, it will come back around and brighten and grow a tail, and someone will see it first. They will not be anyone we know. None of that requires anything from us. The dust is already on the road. It has been laid down through thousands of years by an object that has never known we are here, and it will keep arriving in August, whether the sky is clear or overcast, whether anyone goes outside,
whether anyone remembers what it is. So there is nothing to stay awake for. The sky will do this again tomorrow, and the night after, and for weeks. It has done it for 2,000 recorded years, and for a great many more than that, unrecorded. It is not going anywhere. Neither are we.